Okay, this is lesson 5. Oh, here a little bit. This is our lesson 5, assignment number 5, right? Workshop number 5. And our objective in this class is to trace equipotential lines. Of a set of any point charges in the plane. In these simulations, we're going to make these equipotential lines in the XY plane. And you guys have already seen this before in workshop number 3. We made surface plots of a set of point charges, right? And we represented the surface plots as dependence of the potential on the XY coordinates. So we put the phi function on the z-axis, x and y is the plane. So for a set of point charge, we have something like this, like mountains with those summits here, close to the charges. And if we saw these surface plots from top, if we trace the contour plots associated with the surface plot, we would see something like this, right? You'd see the equipotential lines. So you could see very easily, just making a contour plot of this function, we'd see the equipotential lines. Okay. Now we are going to use the same approach we did with the E fields. To trace the field lines, we are going to use difference equations again. Okay, we're going to do the equipotential lines using the same approach we did for E fields, which is the difference equations. And the principle is very simple. The E field, if you study electromagnetic theory, is well known that the E field is related to the potential distribution by the gradient, something like this. So this is the same as to say that the E field is orthogonal to the equipotential line, which are the traces obtained by constant potential, right? So that's the principle. The E field is orthogonal to the equipotential lines. Then we have this. This is how it looks like. The field lines like this. The equipotential line is always orthogonal to the field lines. So the principle is very simple. The dot product between E and the increment along the potential lines, the potential line is 0, these are orthogonal vectors. So we are going to represent the fields in MathCAD notation, okay? Increment is a 2-element vector. This is a vertical effect. I mean, the L is like this. The L is a 2-element. In MathCAD, it would be something like this, right? The X, the Y. Or if you want, like this. To save room, I'm using this notation here. The E field is like this. So the dot product is obtained simply by doing the matrix product. For instance, if I make the dot product between E and dl, this is the same as to say E transposed times dl equals 0. E transpose like this, dl is like this, so we have ex dy, dx dy equals 0. So this is the same as that. Okay. So what you get is that ex dx plus ey dy equals 0. So you have a differential equation, which is dy dx equals to minus ex divided by ey, right? So notice that this is a very simple equation. As before, for the field lines, the equation was slightly different. We had dy dx in direct proportion to ey over ex, right? So there's a change here. The sign has changed and the ratio has been inversed, right? So to solve the equation, if we start the equipotential line at a point x0, y0, the solution of this equation here is y equals y0 plus integral between x0 and x. Should be a minus sign, right? Here, sorry, it's supposed to be minus now. Ex calculated at on the equipotential line xy point divided by ey dx. Okay, so that's how you calculate mathematically, or because we don't know where the field line is, we cannot calculate this. So we have to do by iteration. We again define a discrete variable k, start from 0. Okay, 1, 2, etc. And we iterate the x variable, xk plus 1 equals to xk plus an increment that is predefined by you. I mean, depending on the size of the domain, make the x very small relative to the sign. For instance, it could be 1/10,000th of the domain or something like that. Okay. And then you just make a different equation. Yk plus 1 equals to yk minus ex calculated the previous set of points divided by y, xk, yk. So it's very similar to the program blocks you developed for the field line. Just make a slightly different equation now, times delta x, right? We have to be a little careful now with the question of bending of equipotential lines. Is a little different than bending of field lines is one way. Bending of equipotential lines, different properties going to take place. If you look at the bending of equipotential lines, you have to be careful now. This is a bending, okay? This is a bending of an equipotential line. Now, in the bending, recall that E field is always orthogonal to the equipotential line. So, in a bending, x is increasing here. When you get to a point, a bending point here, then x is supposed to decrease. The component of the E field that is changing sign is EY now, not EX as before. EY was down, now it's up. So there's a changing sign in UI that corresponds to a vertical band of the potential line. I mean, a horizontal band like this is okay, because the x is always increasing, it keeps increasing. But a vertical band, the x has to change sign, okay? And the component of the E field who determines the changing sign is UI, okay? So that's the difference you guys have to look in this new assignment. That's the modification and the logic of the problem. It's just UI who is going to change sign. We are not going to have any problem with the sign of the charge, okay? In the charge, I mean, in the E field plots that we did before, we were very concerned with the E field that the E field get away from the charge, right? That was our concern. So we were very concerned about the sign of the charge to guarantee that the field line didn't get close to the charge. Now, the equipotential lines, they don't have any problem. I mean, if it has a charge here, if you have an initial point here, it's not going to go towards, it's going to be around the charge, okay? Something like that. So the equipotential line is going to look something like that. I mean, something like the scene here, okay? Several charges have several equipotential lines. And if you see, I mean, the E field will be orthogonal to these lines somehow. So the objective of this new assignment is for you guys to implement a block to calculate the equipotential lines all at once for a set of charges. All the equipotential lines, you're going to pile those in a single output block, which is called the equipot. The name of the block is going to be equipot of P. P is the parameter matrix that was defined in assignment number 4, which has charges, the sign effect, like we just use unit charge in the simulation, right? And the coordinates of the charges, right? That's what we have. This is the same definition, okay? So equipot is going to know this value, but this is going to be an input. It's going to calculate all the equipotentials associated with the charges, put them all into, in fact, equipot is something like this. It's a two-column matrix, which this has all the coordinates of the equipotential, the x coordinates, all the y coordinates, so you plot y versus x, point by point, not line, okay? Because line is going to put together all the equipotentials that are not related. So put points, you can see by points the equipotential lines. In fact, in this assignment, we are going to plot the equipotential lines together with the field lines. So you see the orthogonality property, okay? Now, the question now is, when we did the field lines, we started on different points, if people recall, close to a charge. And we defined an azimuth angle, where you could trace an initial distance of, let's say, 0.1, and then we would start at this point at a given angle from the charge, and we would start plotting the field lines. That's how we did in the field lines. So you go a 0.1 and start from a distance 0.1 according to a given azimuth phi. Okay? That's how the field lines were traced. Okay? Now it's going to be a little different, because field lines are not the same as the equipotential lines. So what are the initial coordinates? How do we define that? Okay? So these initial coordinates will all be put together in a matrix called W, which depends on the locations and charges. In fact, W doesn't depend, it depends on P, but I mean, only depends on the XY coordinates of the charges. Okay? These are the initial coordinates of the system. So your program will know the matrix P, will calculate according to the prescription I'm going to give now, this all initial coordinates put together in a matrix, and then at the end calculates the equipotential lines based on this information. Okay. Well, how do we define the initial coordinates? Well, we do it in a certain simple way. If you have a set of charges, one way to trace equipotential lines is to determine the center of the system, the centroid of the system, and define lines that go from the centroid to a given charge. If I know this line, and if I just separate in regular intervals, okay, I can start the equipotential in each of these points along this line. For instance, I could determine the centroid of the system, divide this line in 5 equal parts, okay? So I have 1, 2, 3, 4. The 5th part is on the charge. So I start my first equipotential here, my second equipotential here, my third here, my fourth equipotential here. So I have 4 equipotentials associated to charge Q0. I do the same for the other charge. I go from the center of the system to that charge, divide in equal parts, and start the equipotential here, 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 here. So I'm going to have all the equipotential space like this. Okay? So what we have to do is, first, calculate the centroid of the system, which we call the Ym vector, which is simply the mean of the vectors. Okay? 1 over n, summation from n equals 0 here, in fact, not n equals 1. We start labeling at n equals 0, right, in math cat. So n equals 0 to n minus 1. So Yn are the vectors associated to the positions. Q0, Y1 would be from here to here. Y2 is from here to here. We sum this vector, take the average, you're going to find Ym. Okay? So first part calculate the vector that defines the centroid of the system. Then calculate this vector here that goes from the centroid to the nth charge. So what we have to do? Make the difference between this and that. To calculate this difference, you have the vector that goes from here to here. If you make the difference between this vector and this one, so we have this vector here, and so forth. Okay? So when you find the xy vector, which is the difference, which is the one that goes from the centroid to the charge, so you divide this in equal parts. Let's say, if you want to say 5 parts, you make a delta xm, which is this divided by 5. Okay? Calculate xm. Then calculate the increment, delta xm. Then you can calculate each initial coordinate in a very methodological and simple way. Okay? K equals 0 is this one, K equals 1 is this one, K equals 2, K equals 3, and so forth. Okay? So you define K values of initial coordinates. So these are the equations for a given charge M for a given point in the line between that charge and the centroid of the system. So you have all these vectors here, then you put them together and you find the parameter W, okay? Which is this one. So at the end what you have, W is going to be the first coordinate of the equipotential associated to first charge, etc., to the K minus 1 interval, define the K minus 1 interval. They go to the next chart, then you have this set of initial coordinates, which correspond to n times k, a matrix which is we're going to have W. This is, let me see here. The first index is the nth charge. The second index is the index K, okay? Which is the point along the line. First point, second point, third point. First point is index 0. So you have V charge 0, 1, etc. Suppose that is 5, okay? It's going to V, V0, in fact, 0, 3. So we have, if we divide in 5 equal parts, we have only 4 points, okay, between charges. We don't want to end on the charge, so that's why I go until 3, 4, 5 charges. So this is, okay, so you have, this is x0, y0, and so forth, okay. So you go to the next charge, v1, 0, etc., v1, v1, 3, until you have the whole set. So you're going to end up with n times k columns. Okay, your matrix is going to be 2 rows. For any charges and k points between charges, you're going to have n times k initial coordinates. Okay? There's one small logic you have to be careful. If the charge is located exactly on the centroid, this might happen. Okay? The charge is on the centroid. You don't have to calculate the potential associated to that charge. All numbers will be reduced to 0. Okay, if you see here, if the charge is on the centroid, these are equal. Okay, these numbers are equal, so this is 0. So you don't have to calculate anything.
The M in subscript are matrix.
The M.
XM.
XM is a vector. Okay, because these are vectors. Charge location and centroid of the system. Okay, if the charge is on the centroid, this is going to be 0. You don't have to calculate the potential associated with this charge. So you have to know that if the charge is on the centroid or not. So if you have a charge on the centroid, your matrix is going to be a little less. It's going to be your matrix is going to be n minus 1 times k columns. If the charge, one charge, is on centroid, right? So I have to make a small logic to say, well, is there a charge in the centroid? Yes. Don't calculate any potential for that charge, just for the remaining charges. Okay? So, I mean, all you have to do, I mean, is a solve difference equation in a way that you guys already did before. And the other thing is implement a block to calculate this WP, which I'll make a suggestion here for you. Okay? Small program block. I mean, you calculate the formula, you calculate the coordinates, and you just pile together, you know, the initial coordinate using augment in this block here. It's something that you did before, and I showed before something like this. You just do, I mean, you just scan all the charges and all intervals and keep piling what you find as the coordinates. You calculate according to the formulation and just pile together. Okay. So at the end, you have those 2 blocks that you have to calculate. You're going to calculate given P, you are going to calculate WP, which is initial coordinates of all equipotential lines. And from that, you calculate equipot of P, which is all the coordinates of all the equipotential lines of the system. Okay? Which is going to be approximately n times k equipotential lines, nk. Right? It's going to be nk equipotential lines. Each equipotential line has a lot of numbers, so it's a long vector. Okay? And you plot the second column against the first column. Right? So after you do this, the assignment is to plot together equipotential lines and field lines for the examples of assignments number 4, examples A through E. So we're going to do the same thing, plot together and see the orthogonality. Be careful when you make plots in MathCAD. You have to make sure that the space in the vertical direction is exactly the same as in the horizontal direction. Okay? I think I told you this before. You have to scale the plot in such a way that the horizontal size is equal to the vertical size. To make so, otherwise you would distort the space. Okay, you would make the space longer on one direction. You don't want to do that. You want to make sure if you scale the plot, you just measure with the ruler. Okay, you just go there. How many centimeters are here? 5 centimeters. This has to be 5 centimeters too. So scale like that. Okay. So otherwise you would be distorting this geometrical space. Okay. No astigmatism. I mean, you do the same thing in the two directions. Okay. So I think that's what I had to say today for this new assignment. Guys, have any questions regarding this one or the previous one?
You show that yn and
Yn
is
is
in bracket, but ym is not in bracket.
because yn is a function of n. Okay. So in other words, I mean, if you get P, the nth column of P is going to be equals to Qn, Xn, Yn. So Yn is going to pick up this nth column of P. So it's going to know which column it is. I mean, it depends on this. And get a submatrix with the two elements here. So n is an argument. Is a function. Y is a function of n. So if you put n equals 2, it's going to pick the right column. Put n equals 3, it's going to pick the right column. That's why you have to have that. M is just a letter. It doesn't have any meaning here. Y on the side of M, there has no, it's just a name. Okay? You can put any name, just a name. Just to say that it's a medium value. Just M to say that.
This m just distinguish these two y. This m just distinguish these two
Yeah.
y.
Or if I use y minus y over n, MathCAD is going to give an error because it knows that y is used for this function. You cannot use y again. So I have to make a different name. Y prime, I use ym. You cannot use the same name for the same vector. Okay? Going to be true, as she said. Any questions? Further questions?
Yes, for this exercise.
Okay.